Let's start with some very basic algorithm in the machine learning that is called linear regression. As the name suggests, that it is linear. So linear will be in predictor variables like displacement, HP, and weight, and also in the coefficients. It is linear. Regression, I told you why is it regression problem. So for the linear regression, there are some assumptions, but basic assumptions I am just going to tell you what is the basic assumptions for the regression. Basic assumptions for the regression is linear relationship between the independent and the dependent variables. That is the first thing, because it is linear regression. Second thing is there should be normality in the data. Normality means what does normality means? You find the errors between the actual values and the predicted values. Those errors should follow the normal distribution. It should be normal distribution. You must have read about the Gaussian distribution, normal distribution. Mean as 0 and standard deviation as 1. So error should be normal, right? So you should check it out what it is exactly. And then there should be no multicollinearity. What does that mean? That means that if we say in this data frame we have this HP weight, so these are three predictor variables. These should not be exactly correlated. Not exactly even means there should not be a very high degree of correlation between them. By correlation, what do I mean? I mean to say that, say, displacement is following the same pattern as HP. It could be correlation. For getting the exact how to calculate that you can calculate using the function for, and take the two variables between which you want to find the correlation. That will be like between -1 to 1, and if the correlation is 0, that means there is no correlation. If the correlation is 1, that means they are very highly correlated. So okay, so also homoscedasticity, that means there should not be an increasing variance in the data. Like in the errors, what happens is you found the errors in the between the actual and the predicted variables, and then these errors are following an increasing pattern as a function of the predictor variable. That should not be there. The variance should be homogeneous across the whole predictor variable. Also, there should be minimum outliers. Outliers means there are some data points which are not having the proper data. They're misguiding the problem, misguiding the modeling. This data may be wrong because of many issues. Maybe it is some typing error or some problem in the source of the data. That we are not concerned about it. We are just concerned about it that there should not be outliers. If there are outliers, you need to remove it. You need to know about the basic outlier analysis, where we just take the distribution of the variable, and we remove all those data points which are very far away from like 1.5 times the interquartile range of the distribution. So that is a different thing. That is not too much relevant for right now, but I am saying that there are basic assumptions that has to be kept in mind before when you are going to apply any kind of linear regression. So let's just take this data object like df. This is df, and this is the syntax for storing this data set, empty cars. And what you do is empty cars, and this is also here you are telling the variable names which you are wanting to store. So this is the way of writing storing the data object, data frame into this, say, df. So now if you see the df, it looks like this, and it is also stored on the right hand side. You see df, the same thing which I showed you earlier. Now if you have to, what you want to do is you have to you want to convert it into data frame, like as dot data frame df. So if you're not very much familiar about that syntax which are being used in R, that you should read it. I'm just telling you about what is machine learning and what is the basic linear regression problem, how you do it, so that you just get started to know that how you can build your knowledge on machine learning gradually by implementing it in practical problems. Uh, so let's see plot this data frame. If you see on the right hand side, what is this? It shows the relationship between the variables like mpg and displacement. This one, this box. So as the disp is increasing, the mpg is going down. It is showing that there is some relationship. Not, we cannot say linear, but there is some decreasing pattern in that. But of course, we can fit some line in that, right? So nobody is stopping you from fitting a linear relation between this, although this will not be very perfect because this is not exactly linear. So but anyhow, if we are fitting a linear, we will be getting some kind of explanation of the data points variation of mpg with respect to disp. If you see mpg as varying with the if you see mpg varying with hp, that is also linear, it is falling down like this. mpg as weight, this is falling like this, also linear but decreasing. If you want to see disp and hp, this is the box. You see this, they are very correlated, but we will not be going into that thing, correlation, multicollinearity. We are not talking about that, but it's just to know that what is the relation between the variables. It is like that. hp and the weight w, this is like this, and you see that this is an increasing pattern. So here you can see the relationship between all these variables. And what we are going to do is we want to predict mpg as a function of disp, hp and weight. Let's see something how we can do this thing. Say we just want to see just the relation between the mpg and disp. We write like that, and we again see it's just a subset of that data, that plot. It's showing again the linear, some relationship which is decreasing, and as the disp increases, mpg is falling down. Now let's fit this model, and let's store that model in the name object model. LM is the function which is being used for linear regression. mpg is the response variable, and disp is the predictor variable, and this is still which you want to write. This is the syntax, and data is the data df, which is here, which we have stored this whole data in the df object. If you do like that, model has been fitted right now. So what we have done is we have seen here mpg is falling down as the disp is increasing, and what we are intending to do here is we want to fit some line which is trying to predict the mpg on the basis of disp. So let's see how this model has behaved. See, like if we write as ab line, so what I was saying is it just so AB line model, if you do like this, you see that we have fitted successfully one model to this data, and then this data, what we are doing is we are predicting mpg on the basis of disp. This is just a simple linear regression. Regression is because we are predicting the mpg variable, which is very continuous, and we can see the data points are all across this range between 10 to 40. And this continuous variable has been predicted on the basis of disp, which is varying from 0 to 500. We could have seen that initially that the pattern is something falling downside as the disp, and we are trying to fit a simple linear regression model, and we have fitted this. We can see that this line is going in the middle, which is saying like finding the best fit on the basis of the mean value at each point. Like say in this disp value, we have two data points like this and this. right? So it will take the mean value or something like that, and it will just go take this value. At this point, what it is doing is it is taking all these three values and finding the middle value, some mean point. At this value again, it is trying to find some middle value. Like all these values, it is trying to fit a line, right? A line which is trying to explain the maximum of these kind of variations. Of course, this line cannot go through all the points, because if it is going through all the points, then that will not be a straight line. So we have to fit a straight line. So it's not possible for a line to go through all the points. A line might have gone through 2 or 3 points or 4 points, but cannot go through all the points, because so much of variation is there across this line. So it is trying to fit a best line based on the optimization of this model, so that what it is trying to minimize, that's the thing which we should know. See, at this point we have actual value as this or this, but the predicted value is this. So error is this and this, right? At this point, what we have, only one data point. Actual value is this, predicted value is this. So there is of course some error in prediction. What we want to do is we want to minimize these errors, and this line is actually minimizing the errors. If we would have fitted this line instead of here, we would have fitted line here, then the errors would have been increased. Instead of this line, we would have gone through here, again the errors might have increased. So there are so many of options available, but this is the best fit which the model has tried to optimize on the basis of the errors, tries to minimizing the errors. So what it is doing is it takes the error at each data point, like this. These are errors. These are positive errors because actual minus predicted. These are negative errors, like actual minus predicted, because the predicted is large. So this is negative errors, this is positive errors. So if we just add all these errors, then that is positive errors and negative errors will be cancelled. But no, negative errors is also an error. So if it is being added to the positive error, that should not be decreasing the total error. Instead, that should be increasing, because anyhow positive or negative, both are errors. So what we do is we square them. So we square all the errors and then we add it. But since we are interested in the errors, we should square root again. So what we do, we first find the errors at each of the data points, then we square it, all the data points errors, then we add them, and then we square root, so that we get the dimensions of errors. That is called root mean squared error. Root mean squared error. That is RMSE. That is the metric used for optimization of the linear regression. So this is the simple linear regression, right? Now, instead of fitting this MPG on the basis of just displacement, we could have also done like this. Let's copy and then let's copy and then paste again. And instead of just this, we are just adding one more or two more variables, HP and weight. We can write like this: this plus HP plus weight, predicting MPG as a basis of this. Now model is like this. Now if we write summary, check the summary, how to see the summary. Let's see here. The summary of the model is showing like call is like this, the same thing which we wrote above. Residuals are the errors, nothing like the errors which I explained you. Minimum error is negative, minus, I told these are negative errors, and positive errors are 0.5, 0.8. Coefficients are like intercept. Intercept is what? This is the intercept. If you see the plot, this is called intercept. Intercept around 28 or something like that. All right. Y intercept. Just a moment. Yeah, so this is the intercept not for this plot, because this plot was for only for disk. This intercept is for MPG as a function of disk and HP and weight. So this is in four-dimensional. This is in four-dimensional space, right? Initially, it was only a one-dimensional, like a disk is MPG is as a function of disk. Now it is as a function of three variables. So there are total four variables. One variable is MPG, and other are the three variables, which are the predictor variables. But this is the intercept. Similar to this one-dimensional case, this is the intercept for the one-dimensional case, and this is the intercept in the four-dimensional space. What it is like standard error. It is telling that what is the errors in this estimate, because see, instead of just fitting this line, we could have fitted a little above, a little lower. That would have also given me some kind of explanation of the variance. So there are different estimates, like intercept could be like this much, or could be like this much, depending on the lines fitted, right? So we have some kind of variation in the estimates also. So this is the variation, standard error. And then what we try to do is we find the mean value of the estimate, and then try to see how far this estimate is going from the mean value. If it is going too far from the mean value, then it is a signal. It is, so how we calculate this t value, I will explain you. Say, consider the estimate for the disk. It is minus 0.00937. Had this estimate be 0, exactly 0, then the coefficient for the displacement will be 0, right? What we try to see is if the coefficient, these estimates are far away from 0 or not. So what we do is we subtract from 0, like 37 minus 0 divided by this standard error will be giving this t value. So if these estimates are far away from the 0 value, then that means it is significant variable. So like this, it is almost 0. What we try to do is divide by this minus 0 divided by standard error, that gives t value, and t value is very small. So these are called p values. P values should be very, very small. So p values are calculated on base of t value. The t value is very high, that means the estimates are very far away from 0, much deviated from 0, and that should be the case, because as we want some estimates which are not exactly 0 but different from 0, because if the estimates are 0, that means the coefficients of that variables are 0, and if they are 0, then that means the model is not using them as a predictor variable. So instead of getting this exact values of estimates, we try to find the p value based on the t value, and t value is found from these estimates and the standard errors. So we take this estimate, subtract it from 0, divided by this standard error, we get the t value, and the t value is very large, your p value will be very less. So this is the whole process. Instead of this is the statistics behind this, but what we can exactly see, instead of these are the coefficients we can see, and we can see the p values. If the p values are very small, that means this variable is significant. So intercept is very significant. It is shown by star also, that is very, very significant. Then this variable is also significant. Then this variable is also significant. This is the highest significant variable. Then this is the second most, and this is the third most, and this is not significant at all because the p value is almost 1, right? It is 0.92. So this is not a significant variable. Why it is not a significant variable? Because it might be of various reasons, because this may be correlated with one of these variables, or it could be that there is no relationship between the MPG and disk, which can be explained by the linear relation. So this is the explanation for all these variables, their estimates, their standard errors, and t value, and the t value should be high and the p value should be small. These stars show the significance of the variables. Now what we see, these are the codes shown. 3 star means very significant, 2 star lesser significant, and this more lesser significant, and no star means that it's not significant variable. Residual standard error is shown, and a multiple r square. That means that is explaining that how much of the variance is being explained by the variables. 82.6% of the variance has been explained by this model. Adjusted r squared should be lesser because it is telling about if we add one more variable, has this multiple r squared decreased, increased or not. So it is telling that. So adjusted r squared should be lesser, right? uh, Now this is f statistics that is used for judging about this model, whether it has improved or not, whether this model is significant or not. These p values for finding the significance of these variables in the model, and this f statistics is being used for finding the significance of this whole model. The p-value of this whole model is 8.65 minus 0. So this p-value is also very small. That means the model is significant. We can say this from the FS statistics that the model is significant. Also from the multiple R squared, we can say that 80.68% of variance has been explained. And from these stars, we can say that these variables are important. We can remove the disp variable from the model by just fitting again the same model by LM MPG, removing the disk and just writing HP and WP. So I hope that you got very basic understanding of all those things. Might be there are some errors which I might have told while discussing. Sorry for that, but you could check it, double check everything, and but I am sure that you would have by now you would have got the best and a very good understanding of what is machine learning. If you're just a beginner and wanted to know that what we are doing in machine learning, so this is just a basic algorithm which you could start with and start to know about how to learn this machine learning. Just take one algorithm like linear regression, try to understand the statistics behind it, and then you will understand all the things. So it's not a one-day thing that you get to know everything on in one day. It's a trial and error thing. You just keep on doing, read the theory, do the practicals like this, and then if you stuck at some point, you're not getting something, just read the theory again and you will learn it. So thanks for watching this video, and you're always welcome to comment and like